All right, hi guys. We're going to be talking about energy transfer in this video. Just to let you know, my notes for all of meteorology are online. You just have to go to class documents, go to Unit 7, and go to notes for Unit 7. So that's right here. And I'm going to be doing um, a little bit of this set of notes right here on energy and insulation. So let's start here. Um, in the video I'm about to show, they're going to talk a little bit about energy transfer. And they're going to say an important statement, which is right at the very beginning of this.
To look at our planet, its systems, and their energy flow. Earth's physical systems include the atmosphere, hydrosphere, lithosphere, and biosphere. Energy moves in and out of these systems, and during any energy transfer between them, some is lost to the surroundings as heat, light, sound, vibration, or movement. Our planet's energy comes from internal and external sources. Geothermal energy from radioactive isotopes and rotational energy from the spinning of the Earth are internal sources of energy, while the sun is the major external source, driving certain systems like our weather and climate. Sunlight warms the surface and atmosphere in varying amounts, and this causes convection, producing winds and influencing ocean currents. Infrared radiation, radiating out from the warmed surface of the Earth, gets trapped by greenhouse gases and further affects the energy flow. The sun is also the major source of energy.
Now, based upon that video, one really major thing that you're going to have to know, and I'm guaranteeing you're going to see this question in the future, the idea that all, or I should say, the primary source of all of our energy comes from the sun. And the sun is what drives meteorology. It's what gives the atmosphere its energy. And that energy gets here through the form of radiation. And radiation travels through space. And if you think about this, I mean, the Earth and the sun are 93 million miles apart, and it takes like 8 minutes for that energy to transfer here. And it travels through outer space, which is basically a vacuum. So there's nothing there. So it has to be transferred through this process of radiation between us and the sun. It's through radiation. Once it gets here, that energy is going to be transformed into different types of energy, like convection and conduction. And most of the atmospheric energy in our atmosphere, that's redundant, but most of the energy transfer in our atmosphere is through convection. Okay, so we have three different forms of energy transfer, as you can see here, and energy flow. The first type is conduction, next is convection, and the third is radiation. Now, if you look at the picture of conduction, the person foolishly is touching the hot light bulb, and obviously when you are in contact with something hot, there is an immediate response by your body to take your finger away from that hot object because energy transfers really quickly through the process of conduction. And conduction means you're in contact with that object. Convection is the movement of material, movement of fluids due to differences in density. As hot air is essentially made right here above this hot light bulb, the hot air molecules are going to expand, they're going to become less dense, and they're going to rise towards the hand in this picture. So that's convection. It's movement of a fluid due to differences in density. Radiation is the transfer of energy through electromagnetic waves through space in all directions. And if you think about like a big campfire, you can feel the radiation from a campfire from far away. You're not standing above the campfire, you're standing off to the side, and you can feel the heat from something off to the side. Okay, so those are the three different types of energy flow that you're going to have to know. Now, I'll just go through them really quickly again. Conduction means you're in contact with something hot. Okay, so you're touching something like a hot stove. In this case, the Bunsen burner is warming up the metal rod right here, and the atoms in the metal rod are getting hotter. As they get hotter, they vibrate more and they collide with each other. And those collisions, that's conduction, as they collide with each other, they transfer energy all the way down the line, and eventually it gets hot down here. Okay, and depending upon the substance that's getting heated, it'll heat up faster or slower. If it's a metal rod, it's going to heat up pretty quickly. There's a lot of energy transfer through that metal. If it's a piece of wood, not so much. You can hold a burning piece of wood and you're probably not going to feel any thermal energy down here. Okay, at least not very quickly. All right, so that's conduction, when you're in contact with something hot. Convection, again, is the transfer of energy by movement. And this is the really, I would say, the most important one. We have movement of energy because the particles in that fluid, whether it's a liquid or a gas, they're moving from place to place due to differences in density. Okay, so if you take a look at this picture, the molecules of water that are getting heated right here are moving upward because they're becoming less dense because they're hot. And then when they get to the surface, they start to cool off and then they sink back down again. Okay, and so you have this big convection current that's being made. And I'm going to demonstrate that. I'm going to show you a couple of videos to demonstrate convection right here.
I'm going to try to show you a demonstration of convection. This is a convection box. Inside of the box there is a candle obviously burning, and directly above the candle is a tube where the air inside is rising because it's less dense as it heats up. Obviously you can't see that air moving, so I'm going to burn some incense, which hopefully is going to produce some smoke. And that smoke is going to be sucked into the box and then rise out the other side.
Okay, last type of heat transfer is called radiation. Radiation, again, is the transfer of energy through space, through it could be a vacuum, but through a space in general in all directions. So if you're standing off to the side of the campfire, you can feel that heat being transferred to you through space. Okay, so this is radiation here. And actually, all three pictures are shown. So you have conduction, the metal poker here, that's stirring up the fire. That's metal. So you have conduction. That's why the person is holding a glove. Convection, holding your hands above something. You warm up your hands in that way. And then radiation off to the side. Okay. Now, the hotter the campfire, the further away you can feel it. And obviously, the sun is extremely hot, and you can feel the thermal energy from the sun from really, really far away. Okay. All right, now, how does all that energy by radiation transfer to us? Well, the sun puts off a whole spectrum of energy. We call it the electromagnetic spectrum, also known as the EM spectrum, okay, electromagnetic. And this picture is actually in your reference table. We're going to take a look at this a little bit more in depth later, but the electromagnetic spectrum ranges from what we call gamma rays all the way through radio waves. Now, visible light is what we are really focusing on a lot, but also ultraviolet and infrared are going to really factor into our atmosphere and what's happening at the surface with meteorology. Gamma rays, X-rays, pretty bad stuff. They have a very, very short wavelength and they can be very damaging to human cells. Microwaves and radio waves, much longer. They can be damaging, but radio waves aren't going to harm you in any way whatsoever. Okay, you've probably heard of all of these, and in some way they're related to each other because the sun puts them all out, but they're different from each other because they have different wavelengths. So over here we have gamma rays, which have a very, very short wavelength, And you remember wavelength when we talked about ocean waves, very short distance from here to here, okay, from the peak to the peak. Radio waves, extremely long wavelength. We're talking like a meter long, whereas these ones are really, really short. Okay, so the only difference between these is wavelength. Long wavelength over here in radio and short wavelength over here in gamma. Okay, now then the visible light spectrum, which is right in the middle, it's a very short amount of the spectrum altogether. Violet has a very, very short wavelength, and blue, and red has a very long wavelength on this side. Okay, infrared, it's like beyond red, that's what that means, is to the right of that, so it's got a longer wavelength than red light. And ultraviolet, like beyond violet, above violet, they have a shorter wavelength than violet light. Okay? All right, now, most of the radiation that actually reaches us on the surface is in the visible light and infrared spectrum. And when you think about this, I like to think about visible light as just, what you see, whereas infrared it's really related to thermal energy. It's related to heat. Okay? And you can kind of consider that infrared is usually dealing with heat. Our atmosphere is great at stopping the bad radiation from reaching us at the surface. Most of the upper atmosphere is experiencing all those forms of radiation. In fact, if you're in outer space, you're getting it all. That's why they wear those fancy spacesuits and why they're in the protected shield of the International Space Station. It blocks all that stuff. But at the top of the atmosphere, you're getting a full gamut of all those harmful types of radiation. But when you go down through the atmosphere, it starts to block it all out. All that atmosphere, all the molecules in the atmosphere block out that bad radiation. I'll show you a picture of that in a second. This picture here shows all the types of radiation that are traveling through Earth's atmosphere. Obviously, these gamma rays and X-rays, which can be pretty damaging, are blocked all the way down to the stratosphere. They're blocked. They don't ever reach the surface. Everything in here, ultraviolet, visible, and infrared. It's a good thing visible light comes all the way through. Otherwise, it'd be totally dark on the surface. Okay. But all these come down to the surface. Radio waves get down to the surface as well. Okay. But these aren't damaging in any way. So you can kind of see where things are getting blocked out. Now, this picture right here is an important one. As you can see here, it's actually flipped around from your reference table. So on this left-hand side, the red light is on the left, and the blue light, purple light, violet light is on the right. Okay, so it's flipped around. Short wavelength over here, long wavelength over here. So just keep that in mind. I can flip this around. It totally changes the picture. Okay? Okay. Last thing to talk about here is insolation. Insolation, not insulation like in your house. That's what like keeps your house warm. Insolation is a contracted word from three things: incoming, solar, like the sun, and radiation. So it is the energy that reaches the surface or reaches the earth in general, insolation. And insolation can change in four different ways. It can be refracted, which is why you see like golden red sunsets and sunrises. It can be reflected and bounces off surfaces, especially like lighter colored surfaces. Like if you're in the snow and you have or you're skiing, you wear goggles to protect your eyes because it's really bright, or if you wear sunglasses, right, on the beach. It can be scattered, especially on bumpy surfaces, or it can be absorbed, which is what you feel when you walk on like your blacktop driveway in the summertime. Okay, so one of four things is going to happen depending upon the surface and depending upon the atmosphere. Now, this is the big takeaway from that. Insolation is often absorbed when you have a dark and bumpy or rough surface. Dark objects, dark colors, and rough or bumpy surfaces. They absorb a lot of radiation and they'll warm up a lot faster. They'll get hotter faster. Lighter colored, like white, okay, and smooth objects tend to reflect. Now let's think about that in terms of like real stuff. So soil, pretty dark color, a forest, kind of a dark green color, and rough and bumpy. Very good at absorbing, okay? Lighter colored stuff like snow and clouds and smoother surfaces reflect a lot, okay? So if you have dark, rough, absorbing, light, smooth, reflecting. And that's an important concept to remember. Okay. I'm going to skip over this. All right. One more factor that's kind of important is the angle of the insolation. And this is going to really play a role when we get to some meteorology stuff later on in the year. When the sun is higher in the sky, it's at a steeper angle. It's coming down more vertical, straight down, okay? And therefore, it's more intense. It's like a flashlight. It's shining on it at a more steep angle, a 90-degree angle. The light doesn't spread out as much, and therefore it's more concentrated in one small area. Therefore, it tends to be more hot. Okay, so a steeper angle of the sun would be like during the day, around noon or a little bit after noon. The sun is highest in the sky. Therefore, the strength or the concentration of that sunlight is much more powerful. Therefore, it's hotter. The air tends to be warmer when the sun is higher in the sky. And as the sun drops in the sky, obviously, it's coming in at a lower angle, so it spreads out more, and therefore it's not as intense, so it's colder. So in the morning and in the evening, when the sun's lower in the sky, the strength of that sun or the strength of that radiation is lower. Okay, so the intensity of radiation or insolation depends upon the angle of the sun, so during the day. It also depends upon where you are on Earth. It depends upon your latitude. So if you think about latitude, think about it this way. Here at the equator, if the sun is over here on the left-hand side of the picture and it's shining on the equator, it's more of a direct angle, a 90-degree angle. It's actually 90-degree angle twice a year, which we're going to talk about later. And therefore, it's really intense, and therefore, it's really hot. Okay, now the further up you go north, the lower the angle of the sun, and therefore it's not as intense, and therefore it's colder, which is why the North Pole is cold and why the South Pole is cold. Here in New York State, we're at a 43-degree angle right here, and therefore the sun's angle is not as high in the sky, and therefore it's not as hot as it would be if you went down further south. Okay, so that's an important concept too. All right, questions to answer. Okay, and I might actually have you answer these on your own. Which form of electromagnetic energy has the longest wavelength? And I'll give you a chance to think about that. You're going to have to use your reference table for this one. So longest wavelength, is it A, ultraviolet, B, gamma rays, C, visible light, or D, radio waves? Number 2, which type of land surface will absorb the greatest amount of incoming solar radiation? Absorb. Take it in. Make it hot. Okay? Which one's going to absorb the most? And number 3, the diagram here shows a container of water being heated by the Bunsen burner. What is going on inside of this beaker? Okay, why are the water molecules moving? What does it do to? Obviously, this is called convection, but what is convection caused by? Okay, so that's number 3. Pretty simple. All right, and that's it.